see the reactor, which is pretty fun. The motivations behind this research is, if you look at these two graphs, on the left side is the total energy consumption from the US in 2009. We see that most is consumed by petroleum, and the second one is already natural gas, over here, 25%. So if you look where you use these energies, you see that the most is used, of course, in the industry, and then also already on the second place, it's for transportation. So our research focuses on energy storage for transportation, because these are the two main sections if you look at the energy landscape in the US. And we focus on methane and hydrogen because they're so-called clean fuels. So if you burn them, you don't, especially with hydrogen, you don't produce any emissions, only water. And for methane, you just produce CO2 and not like higher carbons, which can poison or are even more poisoning to the ozone layer than CO2. And also these two energy sources, they are renewable. That means you can not only, you don't have to drill for them, you can also make them from waste. This is currently the US and Canada together, they have like 85% of their methane comes from drilling and offshore facilities. And in the future, they try to go to landfill and biomass, which is then converted to methane. And this methane can especially be used in internal combustion engines, which are designed for natural gas. They are so-called next generation clean vehicles. And you can also use the methane for fuel cells to produce electricity and then drive your car with the electricity. And on the other side, for hydrogen, you can get hydrogen from basically cracking water. The energy from for these process you can get from wind, solar, or nuclear power plants. And this is also used in hydrogen fuel cells to generate electricity and then drive your car. So what do we want from a material which stores our hydrogen or methane? First of all, the cost. We don't want that this material costs too much money. Everyone should be able to afford this. Then one big thing is how much mass of gas this material stores per mass volume, or how much mass of gas it stores per mass of material. So it depends on, if you look at a stationary state, like big tanks at home, you don't care about the mass of these tanks because you don't have to drive them around. In this case, you want a material which stores a lot of gas for the volume because you don't care about the mass. And if you look at the car, it's vice versa. You want a material which is stores transportation systems. So what is the difference between compressed natural gas, CNG, and absorbed natural gas, ANG? If you want to use compressed natural gas in your car to drive, to power the car, you usually need high pressure in these tanks. It's around 200 to 275 bar to get a driving mileage of 200 miles. So that means these tanks are pretty heavy because they have heavy thick walls due to the pressure. And these tanks are also very large and expensive because of the obvious reason, because they are so big and so strong. And the other point is, if you want to fuel it up, you need a multi-stage compressor to get from your gas line, natural gas line, which you have on the ground, to this high pressure to over 200 bar. And you see on the left bottom side, this one here is the trunk of a Honda Civic, which runs with natural gas. And you can see this black thing here. This is the natural gas tank. It almost takes the whole trunk space of this car. So it's not very feasible because you want to still transport something in your car. You don't want the whole car is filled up with your tank. So if you go to absorbed natural gas, the good thing is you can store the same amount of gas at around 35 bar, which means that the tank is very light because the walls are not so thick. And you can make conformable shaped tanks. So what you can do is you can take your tank and put it in the body of your tank, of your car. You don't have to put it in the trunk. You see it over here, it's like a schematic. You can put the tank or half of the tank in the floor of the car. And so you still don't lose storage space in your car. So why do we use activated carbon for gas storage? Activated carbon has a very high surface area. It's around 3,000 square meters per gram. And it absorbs the gas molecules like a sponge on the surface. And these gas molecules, when they are absorbed on the surface, they almost form like a liquid layer. So you can say it's almost a coating from your gas molecules on the surface. So you can store more gas at lower pressure. And to give you an example for this, if you look at these black line here, this is how much you can store if you just compress the natural gas. And this is the pressure at room temperature, is this whole thing. And these black squares, this is if you absorb the gas in activated carbon. So these blue lines show the difference between the compressed one and the absorbed one. You can see if you look at around 35 bar, you can store around 5 times more gas in your system compared if you just compress this stuff. So now I'm showing you, giving a small overview about materials which are out here in the world, which are used or at least studied for these methane absorption. This one shows on the x-axis the gravimetric storage capacity. So that means how much gas they store per kilogram of material, and the volumetric is on this axis. It means how much it stores per volume. And you have these yellow circles, squares. These are all materials we do in our lab, which we produce and analyze in our lab. Then you have, these are all carbon, activated carbons. Then you have these purple ones. These are so-called covalent organic frameworks. These are materials or powders which are made from not really organic. You have organic parts in it, like carbon, and you have also metal in there, and other elements. And then you have these kind of red ones. These are so-called metal organic frameworks. You see a picture of them, what is a schematic down here. So they have these benzene rings, and on the corners, these are different metal groups. And they are used to store the gas. And if you look at these, you can see that our materials we produce, they're pretty good out there. So we outperform most of these materials, except there's one which is kind of similar to what we have.
Elmar?
Yes?
If you're making a tank out of this stuff, do you basically, these carbon, are they in granular form? Is it?
Yeah, I will show this later, but you can do both. You can take this in a granular form and just put basically a powder in your tank, or what we do is we produce monolith out of it. So you have basically, it looks like, I have later also a picture, it looks like a hockey puck, which you can put then in your tank. So it's easier to handle, and also you can densify these materials with making monoliths out of it. But in this case, these are only powders. And these ones here, these circles over here, these are monoliths we produce from our carbon, from our activated carbon. And they are still pretty good. I mean, they're not as good as the pure powder, but they're pretty close. The same here is for hydrogen. These are all powders for hydrogen storage. But you have to keep in mind they are all at different temperatures. Mostly it's cryogenic temperatures over here, and this is at room temperature. And all these materials here, these are adsorbents, so they store the material on the surface. These one over here, they store the hydrogen in a chemically bond. So, for example, here you see that the hydrogen is chemically bonded to the magnesium. And so we are still pretty good with hydrogen, but you can see that it doesn't store as much as methane. To give you some numbers, our best methane performer at room temperature has at 35 bar, it's 202 volume over volume. That means volume gas over the volume of our material. And as monolith, you have still 171. And at 160 bar, it's even 360 volume over volume or 310. This material is already is so good that it is over the DOE target for natural gas storage. So we already fulfilled the DOE target for these materials. And for hydrogen, it looks different. You see we are around 3% at room temperature, and cryogenic is 12%. And we also do a boron doping with these materials because this should increase the storage capacity of our materials, which is around 3.4 at room temperature. And you see for hydrogen, we are looking for gravimetric storage materials, and for methane, we look at volumetric storage capacities. So what is the physics behind these materials? Activated carbon, as I say, that has a very high surface area. And you can see this is an SEM picture of some of our carbons. You can see these are the big grains, and they have these black little holes. These are pores we have. This is why they have such a high surface area. So when the gas molecule, if you introduce a gas to this material, this gas comes, if it comes close to the surface, it feels a van der Waals force which attracts it and holds it, or basically it sticks then to the surface. And the gas already condenses, or almost condenses to a liquid layer. The physics is the same as if you take a gecko and it walks up a glass. It uses the same forces and the same physics to walk up like a window. To give you an overview how much really 3,000 square meters per gram is. So if you take a 40-liter tank and you fill it up with our carbon, it has a surface which is almost, I would say, the whole downtown of Springfield here. You can fit in one tank, 40 liters. So that's a lot. So what are the van der Waals forces? In this case, we have the van der Waals forces. They are so-called London forces, because we don't, both materials, the surface and the molecule, the gas molecule, has not a permanent dipole moment. But what happens is if you get them close together, there's an introduced dipole moment, which then holds them together. So the London force is a very is only a close range force, which you can see over here. It's modeled by a so-called Lennard-Jones potential. So you see, if you go far away, you don't feel any attraction anymore. If you go closer to the surface, you see there's a lot of attraction over here. And if you go too close, it's repelling each other again. So it basically...
That's a potential energy function, right?
Yeah.
As a function of separation distance.
Yes.
So a lot of the students here are first year general physics students, and we've talked a lot about mechanical energy and potential energy, and so that relates there. You would put a system would have a constant energy, right? That would then cause the thing to oscillate.
Yeah.
So
what happens is if you take a molecule, a gas molecule, and you bring it closer here to the surface, you will see that it basically the potential energy over here is the lowest one. So it will stay in one of these oscillates between these two states. It's almost like a boundary you have, you can say. And so how do we measure how good our systems are, or how good our powder is? We measure the so-called uptake, and it's measured usually in grams in grams of hydrogen or grams of methane, or even in mole. You can change it. And we do this by measuring isotherms. And these isotherms, they tell us how much gas is stored at which temperature, and how much gas the system can deliver. So on the left side, this one are two isotherms we plotted for 300 Kelvin and 273 Kelvin. And on the right side, this picture shows you how we determine how much gas we can deliver. So if you take, for example, these blue shaped isotherm, and you say, for example, that your car is still running, that the engine is not stalling, you need around 2 bar, let's say around 2 bar that is still running. So we draw a line at around 2 bar, a vertical line. Everything from the intersection to the right side is what the system can deliver and what we can use. So you can see that the shape of these red isotherm is better because it can deliver more gas compared to the blue one. And you can see that our isotherms are looking pretty close to the red one. So which theory do we use, which absorption theory to describe our materials? We use the so-called Langley theory of absorption for some of them. This theory says that we have only monolayer absorption. That means you have only one layer of film of gas molecules on your surface, and it has fixed size. That means that your whole surface is homogeneous, so you don't have any like impurities in this. And also you have no interaction between the gas molecules, the adsorbed gas molecules. And a typical theoretical isotherm would look like this. It rises pretty steeply and then it almost levels off when the monolayer is saturated in this case. The problem with this theory is that some of our, we believe that some of our material have multi-layer absorption. So that means you have not only one layer of gas molecules on the surface, you have like 2 or 3 layers. So that's why we go to the so-called Brunauer, Emmett, and Teller theory, or BET theory. It is a Langmuir model, but it allows to have multi-layer absorption. Everything else, like the fixed sites and the no interaction between the molecules, stays the same. And these isotherms, theoretical isotherms, they rise very steeply, but they don't level off. You see that they rise here again. This is due to the multi-layer. So you can, this model allows you to have almost, or you can have infinite layers of absorption. So if you work in these absorption section, or if you do research in it, you come across like about 3 different names. There's the so-called Gibbs excess absorption, the absolute gas absorption, and the storage gas. What we mean with excess absorption is the gas which is absorbed on the surface. So it doesn't matter how much gas you have in your tank. Everything which is in the gas phase doesn't account or contribute to the excess absorption. This is a typical experimental equality, so we can measure these. Then you have the absolute absorbed gas. This is everything on the surface, every gas molecule on the surface which is absorbed or not absorbed, but not the gas which is far away from the surface. This is a typically theoretical quality. And the more engineering quality is the so-called stored gas that takes everything into account in your system. So that means the gas phase and the liquid or the condensed phase.
I have a question.
Yep.
When you say that you can get multiple layers, and these are induced dipoles, right? That are okay. So, and that their attraction drops off really strongly with distance. Yes. So, for the second and the third layer, and so on, are these layers actually attracted to the substrate, or are they attracted just to the neighboring molecules? Because it's hard to imagine that you get more than you know.
The theory says you can have infinite layers of this, but in practice you have one as mono or 2 layers at maximum. So what we have seen is that you have 1 or 2 layers on the surface, and some theories believe that the attraction between you have a slight attraction between the gas molecules, but the main attraction is what we feel from the wall. So you can say the first layer, which is closest to the surface, had the highest density because it feels all these potential. The second one has less density again because it's more or less like a shim, or it's like it doesn't see the whole potential from the wall because there's a layer between it already.
Mm-hmm. Yeah.
But the density is still higher than what you have in the gas phase, in the pure gas phase.
it seems like that it would be that second layer would have like incredibly less strength of binding than the first
Yes,
one.
yes it has.
So it becomes very, very weakly bound.
Yes, it's very weakly bound. The main key here is that the density is higher than what you have in the gas phase at this point. But it's not, you're right, it's not really, I wouldn't say, it's really bond, like a chemically bond or something, it's not very strong.
Yeah.
So that's not the case. And to clarify what I say, what I mean is success, absolute and total amount stored, I have this left picture over here. This is the surface. All the red pieces are here. This is the gas which is absorbed on the surface. Then down here you can have molecules on the surface which are not absorbed. This is this piece, that's the number 2. So 1 and 2 together is the absolute absorption. The red one is excess absorption, and the total amount is everything. So it includes the gas phase and every gas molecule we have in there. And you see these different isotherms, you can plot them. This is excess, this is absolute, and this is total amount. The interesting point is if you look at this shape here, it rises and then starts dropping. This drop happens if the gas phase of your gas has the same density or higher density than your absorbed film. Then it starts leveling and dropping off here. So actually we use this drop here to calculate or to see what the density of our film is. So that's why we know that we have almost liquid density in this film. So to have a high surface area, this is not is one of the key points. Another key point is like what I say, you have pores. Because in pores, you have overlapping potentials from the one side and from the other side of your pore. In this case, if you look at a simple model, you take a slip-shaped pore. So you have carbon here and you have carbon here. So you have a potential from this wall and coming and from this wall. And they overlap and they add to each other. So if you plot it, you see the potential looks like this. So you still at the middle here, the potential is not as deep as on the side of the wall, but it's still deeper. You still have a potential, say it this way, which helps to store more gas. Because if you have a deep potential, it means you have more density. The gas is dense. It's more dense. And the same here is if you look at, for example, at an 11 angstrom pore, these are the main pores we have in our system. For methane, you see you can get 2 layers, and for hydrogen, you can have actually 1 layer on the left, 1 on the right, and here on the middle, this is what I call a 3rd layer. So it's not really as dense as directly, if it would be directly on the surface, but it's still denser than the gas phase. This is also another SEM picture where you can see these holes here we have, the pores. And you see these are potential for different pore sizes. You can see if the pore gets smaller, you get a deeper potential, which means you can absorb more gas. But the problem is with these deep potentials that you can't remove the gas so easily anymore. So you have to balance these, how strongly you want to basically bond them or not. So let's go to the methane materials, the methane storage material. Our storage material is made mainly from corn cob. So we take the corn cob, we treat it with phosphoric acid. The phosphoric acid removes most of the unwanted materials like oxygen and nitrogen, stuff like this. And also we have, in an organic material, you have, for example, iron in here, a little bit of iron. This is also removed with the phosphoric acid. So you end up having around 70% of carbon, pure carbon in our system. From starting material has around 50%. But with this step, you still don't have a very high surface area or pores. You just have the carbon vapors. So to create actually the holes, we use KOH, potassium hydroxide, and we soak our material in potassium hydroxide. And this creates then the pores. And you end up with almost 90%, a little bit over 90% of pure carbon in our system. So how does this activation mechanism work? You see over here, these are the chemical formulas. You want to look at them. But basically what happens is we oxidate the carbon, and then we penetrate the carbon layers. The potassium penetrates the carbon layers, expands them, like it pushes them further apart, and then we quickly remove the potassium, and you're left up with almost graphitic layers. The good thing about these activation mechanism is that you use abundant and inexpensive raw materials. In this case, it's corn cob, and also the KOH or the phosphoric acid is not very expensive. Then you can do large-scale productions very easily. You just have to scale it up, basically. And the good thing is also that you don't need a special handling for these carbons. So you can take it, you can just leave it on the bench, basically. It doesn't alter, it doesn't change the absorption properties. This is quite different from, for example, moths. Moths use very expensive chemicals to make them, and you can only make them in very small quantities. So around, let's say, the last what I heard was around 1 gram or less.
What's a moth?
Metal organic framework.
Oh.
This is basically you have organic like benzene rings, and then you attach metals on them as storage material.
Yeah.
So these are very easy to handle materials in this case, because you don't have to care about oxygen or moisture or so on. So we also produce monoliths out of this, and we do this because if you look at the volumetric storage capacity, it depends mainly on the density of your material. And with producing monolith, we can densify this. So if you look at the red dot here, this is 0.3 grams per milliliter, the density. This is from our pure carbon, from our powder. And if you press it to monolith, you can go up already almost to 0.7 grams per milliliter. So we can increase the density by a factor of 2, which also increases the volumetric storage capacity. That's all more or less theoretical, because this is only true if the absorption physics behind there and also the surface is not changed. You have the same surface area, for example. But if you do it in the laboratory, you lose a little bit, but not much by pressing these monoliths. So how we do this is we take our powder, we mix it with a polymer, we press it, and we have a 10-ton press, which we use for this. And then afterwards, we pyrolyze it, and it stays in these, it looks almost like a hot liquid. You see it over here. This is like 3-inch in diameter, and this is 1 centimeter in diameter. And they have a density of around 0.7 grams per milliliter. So the instruments we use to analyze these samples is, we have one, it's so-called the gravimetric analyzer. It can handle samples from 1 to 5 grams at room temperature and goes up to 300 bar. The good thing for this instrument is it's very cheap. You see the whole instrument basically sitting over here on the bench, and you have to do 4 mass measurements, and with this you can calculate how much gas is absorbed with this equation over here. And the good thing is also, if you look at the commercially available instruments, gravimetric instruments, they have to have buoyancy corrections to do all these measurements, and we don't need this. So it's very simple to do this and very quick. Another one is the so-called rapid screening instrument. This is mainly used for quality control. So if you get a large batch of our carbon, you just check it if it has the same quality or not. And this works in the so-called Sievert type apparatus. So it calculates the uptake by measuring 2 pressures. So what you do is you have a system, you have a storage tank, you fill this up with gas. Here you put your sample in there under vacuum, and you open the valve between them and let the gas expand. And from this pressure difference, you can calculate with this equation here how much gas is absorbed. And we have, for our monolith, we have these, an automated Sievert apparatus system, and it also it goes up to 300 bar, and we can test up to 500 grams of our sample. And you see here a glove box. This glove box we use for hydrogen. We use this instrument also for hydrogen measurements. And some of our hydrogen materials, they're oxygen sensitive. So we use this glove box to load the sample under oxygen-free conditions. But for methane, we don't care because it's not oxygen sensitive. And then we have, last but not least, we have a so-called 10-liter test tank system. It holds samples from 1 kilogram to 10 kilogram. And it does the measurement at dry ice temperature or room temperature. And what basically is, you see these white cylinders, and in these cylinders we have metal cylinders where we store our samples in there, and then you put water, or in this case also you can put dry ice around it to change the temperatures. And we use this instrument mainly to test the kinetics, the absorption kinetics. So how quickly can you load your system, how quickly can it release the gas, and what are the temperature differences if you release the gas or if you absorb the gas. And as I said before, this is just our best hydrogen methane performance material. You see again, this is compressed natural gas, this is our absorbed natural gas, and you see the volumetric storage capacity, and as I already stated, 35 bar, we already reached the DOE target. This one goes up to 160 bar, and you see that these materials, they have a very big advantage from 0 to 80 bar. You see this here. These are all the absorbed materials, absorbed natural gas, and this is the compressed ones for different temperatures. You can see the main focus, we focus mainly on this pressure, because that's where we gain most of these materials. And at high pressure, we gain a little bit, but not too much. And this is here for, you see, for the monolith. And again, this is for different temperatures for the monolith.
Wait, which one's the monolith?
This one here is the monolith. This is basically these hockey pucks, these big ones we produce. This one and this one. And here you see the absorption, how long it takes. Basically, we do the kinetic studies. So you see here, and it takes almost 4 minutes to fill the 10-liter tank with gas to 90%, which is pretty good, because that means if you, for example, take it and you use it in your car, you have to wait at most 4 minutes to fill the whole tank up and you can drive. And so you don't have to wait very long. If, for example, if you take hydrogen and you store it at the liquid hydrogen temperature, what they do in Germany sometimes, you have to wait until like 15 or 20 minutes to fill the car up. And no one really wants to wait so long. So this material is pretty good. It's pretty quick. You can see the same is also if you desolve the gas. So it releases the gas very quickly.
People use liquid hydrogen in cars in Germany?
Yeah, BMW does this. It's a little bit stupid because they, in my opinion at least, because they use a combustion engine and just put put hydrogen through it as gas. Because then you don't have to change much on the engine to do this. But they store it in as liquid hydrogen.
How cold is it?
It's below liquid nitrogen temperature.
In a car?
I think it's like 12 Kelvin, if I'm correct.
So they take a nearly conventional BMW
Yes.
engine and then just...
It's a completely conventional engine. They have a fleet of 3 or 4 cars in Munich where they do this. And for these tanks, I know they are, you have basically 2 tanks in it. You have a liquid hydrogen tank, and around them you have a liquid nitrogen tank to cool it down. And it takes 15 to 20 minutes to fill one
You've got
gas.
to be losing on the weight there, right? I mean,
Yes.
You're putting these big, heavy tanks
Yes.
to hold this stuff in the
They
tank.
use in BMW the 7 series, so the very big ones, and basically the whole trunk is gone. The trunk and some of the leg space from the passenger seats are all gone due to these big tanks. And they can, I think they can drive like 100 kilometers or like 60 miles or something, and the whole tank is gone. So it's not very feasible, in my opinion. So just to summarize it, so as I already said, we already reached the DOE target for the methane materials. Let's come to the hydrogen materials. For the hydrogen materials, we also use the activated carbon, the exactly same one we use for the methane. What we do is we sometimes boron dope it, because if you have a boron atom on the surface, it increases the binding energy between the surface and your hydrogen molecule. And we also make the activated carbon from PVDC, from a polymer, and also we use boron-containing polymers to do studies on how actually it changes with different impurities like boron, or we also want to do iron or potassium on the surface to see how this changes. And polymers are very simple for this, because you can really, you know how much impurities you have in there. So how we produce the PVDC activated carbon. First, in our lab, we do the PVDC, the pure, that's pure plastic. So we use the VDC, which is the monomer. Then we use a radical starter. So this is this compound here. If you heat it up, this bond breaks here, and you have radicals, which then attack the double bond here. And in the end, you form these PVDC, these polymers. This is the first step. And after that, you have just a block at this point. You don't have any pores, no surface area. The second step is you heat it up to almost 700 degrees Celsius. And what happens if you heat this up is that one hydrogen here grabs the chlorine over here, and it forms gas, and it's hydrogen gas, hydrogen chloride gas, which then it's very violently, and it looks like at the end like a sponge, so it creates a lot of holes, and at the end you have not a solid piece, you just have, in the end you have graphene sheets over here, and you do this long enough. And this one we did, Simon also did this in the summer. He did studies how the heating range, how if you heat these materials quickly up or slowly, how this changes the surface area. And you see it here, schedule A is this one here. We can create surface areas of around 1,600 square meters. And if you do it, this schedule C, you get around 870. So you see that depending on how quickly you heat these things up, you can change how much surface area you have. And this one is the so-called pore size distribution. So that shows you we have PVDC, we have a lot of pores at around, I would say 11 angstroms. And it doesn't matter how quickly you heat them up, you just end up with 11 angstroms. If you look at the concrete-based carbon, we have a lot of different pore sizes. We have one here, it's around 35 angstrom, then you have around 22, and this is also 11 angstroms. So if you look at the left side, these are two, this is carbon, and this is activated carbon from concrete, and this is activated carbon from the polymer. If you look at these isotherms, you will think, okay, why do we do this? The activated carbon from concrete stores more gas, so it's higher over here compared to this one. But if you take a closer look and you compare it, you normalize the whole thing to the uptake to the surface area, you will see that for lower surface area, the PVDC-based sample stores a lot more, almost twice as much gas, but it has a lower surface area, which is pretty interesting at this point. So the other thing we do is we use boron-containing polymers. For this, the problem is if you have a boron in your monomer, you can't polymerize it with a radical, because the boron will grab the radical, and then you don't have anything to start the reaction. So we do, you have to do a couple steps. First, we produce this compound. This is a monomer from bromostyrene and fluorotrimethyl. This monomer we take and we polymerize this, and then afterwards we exchange it with this BBr3. So what happens is if you take the polymer and you just expose it to BBr3, the BBr3 grabs the silicon complex down here and exchange it to boron bromide, or if you add water to it, you get this compound down here, which is a boronic acid. And we use this to form our polymers, the boron-containing polymers. The other step we do is we take the activated carbon from corn cob and we try to boron dope this, because simulations showed that if you have boron on the surface, you can almost double the binding energy between the surface and the hydrogen. And we do this by using decaborane deposition on the surface. So you take a vessel, you mix the decaborane with your activated carbon, and then you heat it up. And at the end, what should happen is that this decaborane, which looks like this, so these red dots, these are boron atoms, and the white ones are hydrogens. So this cage breaks into pieces, and these pieces should stick then to defects we have. And basically should be chemically bonded then to the surface. You see, this is phase diagram of decaborane, and we do two methods. We go from the solid to the liquid, and then we decompose it. Or the other method is we go from the solid to the gas phase, and then decompose it. And this one are the process distributions for different boron-doped materials. And we can achieve 9% boron to carbon ratio with a single-step doping without losing a lot of our surface area. And we can do, we reached a 7% boron to carbon ratio with a 5-step doping, which also has no effect on almost no effect on the surface area. But with the multi-step doping, you see it over here. This is the red curve. You end up with more pore volume compared to the single steps over here. The black curve is the precursor. This is just the activated carbon. For these studies, we use we built our own instrument, the so-called 20 Kelvin instrument. It can hold samples from 6.5 cubic centimeters up to 24. And it's a Sievert type apparatus, which means that you just measure the pressure difference between before you dose it and afterwards. And from that, you can get how much you absorb. And the temperatures you can see here, we go from 7 Kelvin all the way up to 300 Kelvin and 200 bar. And we use this instrument mainly to do a so-called hydrogen BET surface measurements. So if all these, if I report and if I say we have 3,000 square meters per gram surface area, this is all measured with nitrogen molecules, because these are commercially available instruments. But the problem is, if you look at the nitrogen molecule, it's bigger than compared to the hydrogen molecule. So theoretically, the hydrogen should see even more surface area. It should penetrate into smaller structures compared to the nitrogen. And this is why we have this instrument to measure, to do BET surface areas from hydrogen. And this is our commercially available nitrogen BET surface measurement instrument. And here you see, this is the undoped activated carbon. This is the doped one with boron dope. And you see at higher pressure, it gives you an advantage compared to non-doped one. And because it's at higher pressure, we have an advantage. We think that the average binding energy increases. So the whole surface, basically the binding energy of the whole surface increases, and not like a single dot. And we can calculate the binding energy by measuring 2 different isotopes at different temperatures. And with this equation, the so-called Gaussian-Clapeyron equation, you can calculate how much the binding energy is. You see it over here. This is a binding energy without doping, and this is with doping. You can see we almost doubled it with the boron doping. So at the end, what we can do is we The activated carbon made from PVDC shows a very high aerial excess uptake, so it means it absorbs a lot of gas per surface area, which is unusually high. Then we have, with binding and with the boron doping, we can almost double the binding energy between hydrogen and the surface. And it doesn't do much to the, we don't lose a lot of surface area. So our future work, what we are working on for hydrogen, we want to create boron-doped monolith. Then, as I said, we want to measure the hydrogen surface area. We want to determine the film thickness of some of our samples. And also we want to investigate different boron doping procedures. And for methane, we want to optimize the monolith process, and we want to upscale the manufacturing process. So we want to do kilogram batches at this point. And we have one project which we will do, especially in the summer. We want to make a 40-liter tank. We want to fill it up with our carbon and then test it under road conditions. So that means we will. Our target is to measure, to test it for 100,000 miles, like desorption and loading and deloading of this material. Okay, the last step is the summer school we have. We are searching for research internships from June to August in our department. And you basically will work on some of our instruments. You can do theoretically work. We have a group which only does computational stuff for us. You can work in the chemistry department to actually make our carbons, or you can work in the mechanical engineering to fabricate and design the tanks. And yeah, it's paid. That is all. Do you have any questions? Yes.
Yeah, I noticed, so you've got these two methods of storing natural gas by having it interact with carbon atoms or
and you're comparing it to compressed natural gas.
Yes.
So I want to get a lot of methane stored as compactly as possible
Yes.
in as light a tank as possible.
Yes.
If I think about doing that through these methods, how does that compare with liquid natural gas? Because there's already liquid natural gas commercially available.
Yes.
I drive down to Arkansas and actually